This is Nick Teisler's Lab 9 video for Modern Physics 1 at Georgia Tech. In this lab, we're looking at two-dimensional motion of a mass oscillating on a spring. We are analyzing this motion using the momentum principle, Newton's second law, and the energy principle, the first law of thermodynamics. We began this lab with a video of a mass oscillating on a spring. The motion was plotted in Tracker and transferred to an Excel sheet and ultimately modeled in VPython. In this same file, a simulated mass and spring with the same conditions were coded. The simulated spring constant was set to 6.96 newtons per meter, the value found in Lab 8. L0 was set to 0.1334 meters, a value calculated by using Hooke's law, the knowledge that the weight is 0.402 kilograms, and the fact that when the weight is in static equilibrium, the spring length is 0.7 meters. When I run the simulation, the blue ball you see represents the weight from the video in Tracker, and the orange ball on the spring represents the simulated mass. This graph shows the y position of the two masses over time. The green is the model, red simulation. This graph shows the x position of the two masses over time, same color scheme. From these two graphs, we can get a good idea of the periods of the oscillating masses in the x and y directions. One period on a graph is the distance between crest to crest or trough to trough. On the y graph, using the rollover function on VPython, I got the time differences for the model and simulation periods. The change in time is final time minus initial time. At this point for the simulation, the time is 6.028, and the initial point is 4.512. I'll do the same for the model over here, and we get that the periods are only 0.013 seconds apart from each other. I'll repeat this analysis for the movement in the x direction of the graph. In this case, there is a bigger difference between the model and simulation, but the method of just eyeballing the graph here, even though VPython gives us values when we roll over, is still a crude one. The next step in the lab was to incorporate the spring into the system and look at the changing potential energy of the spring. Here you can see the changing potential energy as the spring stretches and compresses. It's hard to see what exactly is going on, but as the spring is stretching away or compressing towards its equilibrium point, the change in potential energy is positive. At other times, it's negative unless the mass is at a point where the value is 0, changing from negative to positive. The change in potential energy is the actual y value of the graph, not the slope of this curve. Now, onto the what does it mean questions. Firstly, compare the period of oscillation you found from examining the x component of position with the period of oscillation you found determined from the y component of position. Do they differ? They do in fact differ. The horizontal and vertical periods are independent of each other. Imagine having two different springs, the same spring constant, L0 mass, and everything else equal. If you displace the mass the same amount as Dr. Greco did in the x direction only, the period of that oscillating mass would be the same as our x period. Same goes for y. If you displace the spring only in the y direction, the same distance as Dr. Greco did, the vertical period would be the same. For number 2, what does it mean? With your new choice of system, determine the work done by the surroundings. Is the energy principle satisfied? In our system, we include the spring, earth, and mass. The significant energy quantities we chose to include spring, potential energy, mass, kinetic energy, and potential energy due to gravity are all internal to the system. In the graph of the changing energies, the yellow line, the sum of the change in energies, is always 0. This means no energy or work is being added to or performed on the system. The energy principle, change in energy of the system equals work done by the surroundings plus other energy transfers, is satisfied. Our delta E is 0 because no work here is being done by the surroundings and no energy is being transferred into or out of the system. The last how does it mean question asks how the physics of our system changes when we decide to move our origin from the anchor point of the spring to the initial position of the weight. The physics of the system don't change. What does change is the quantity for the total energy of the system. In the original simulation, with the origin at the spring anchor, if you sum all the energies, your number will be less than the sum of all the energies with the origin at the weight's initial location. Because potential energy has to do with interacting objects, you can get different values for potential energy if you choose a different origin. However, I maintain that the physics of the system don't change. The change in all the energy quantities remains the same. The energy principle states that only the change in energy is going to equal the work done by the surroundings, plus any other energy sources. That's why the energy plots still look the same, and also why the bouncing object behaves the same way.